So the point of our project was to see whether the R value, which is rated for construction materials, is an adequate way of comparing different thermal envelopes. The R value is calculated as 1 over U, which is the overall heat transfer coefficient. And since everything we do is in the SI system, we wanted to putting it back into English system, so it's an R value that we are familiar with. You can simply multiply it by 5.68. U is calculated as 1 over the resistance total of the planar wall times the area that is being tested. And our total, or the resistance total, is the resistance of your convection, conductive, and radiation resistances through the plane wall. The competing envelopes that we were studying are ICF, SIP, and conventional. So ICF stands for insulated concrete forms. These forms are a 6-inch concrete core surrounded by 2 5/8 inches of expanded polystyrene on either side, and this forms the structural with the concrete in the middle, and the insulative properties are with the EPS on the outside of the wall. When calculated, it gets a U of about 0.2198, and R value of 4.55, and in English this turns to a R value of about 26. SIPs, or structurally insulated panel systems, also known as SIPs, are a structural wall that uses composite theory to make the structure. And so by having the sandwich structure of OSB glued to the core, it creates a rigid structure, and then the insulation portion is on the inside of the wall. Typically it's XPS foam, even though this graphic shows EPS, and XPS stands for extruded polystyrene, but other varieties of plastic foams are available. In our instance, we used 6-inch XPS core with 7/16 inch OSB sandwiching on either side. Notice its U value is lower than the ICF, and so its R value is higher, and it comes into about a 30. The conventional wall system of studs and fiberglass within the bays is the most common form of construction still, and the R value system was based on the insulation between the bays. So really this is where the R value was designed to be used. The R value for the insulation alone was about R19, but mixed in with the whole U value and taking into account the various external sheathings and things, it comes out to about an R21. The experiment we did was we built a wall segment that contained 3 individual walls, each about 16 inches in area, 16 centimeters by 16 centimeters square. That was the length of or thickness of the wall, and that was placed through a window. And as you can see on the graphic on the left, each of those red dots represents a temperature sensor. We place temperature sensors in the external ambient air, 1 on each surface of each type of wall, 1 in the midplane of each type of material. In the middle, you'll notice we have 2 temperature sensors. We had 1 in the stud itself and 1 in the fiberglass. And then we have sensors on the internal surface temperature as well as the internal ambient. And the graphics on the right are the actual setup of our scenario. We used an Arduino thermometer that measured 12 temperatures simultaneously, and it logged those temperatures every 10 minutes. And we set this over the course of about 5 days, but the data seemed to be corrupted after about the 3rd day. We do believe it rained and messed up the electronics. So the governing equations which we were working with were that the Q double prime of convection, which equals the convection coefficient times the temperature gradient, is the primary source of input of the loss of heat through the wall. And then we also have the Q double prime of radiation, which also takes into account the temperature gradient, but it's to the power of 4. And so our total Q double prime going into the wall was Q double prime in, which is the sum of those two things. And that is for steady state conduction only and steady state convection radiation. Because we were determining whether thermal mass changes things, we needed to do transient. And so taking our Q double prime in to be the input Q factor, we eliminated all those other units in the transient conduction equation, and that would give us the bottom equation that you see there, which multiplied by area, and if you later divide by the rho volume and specific heat, will give you the degrees of temperature Kelvin over per time. And so using a bunch of book values and calculating the H through Nusselt correlations, we were able to develop and calculate the Q double prime total that was going through the wall. And the reason why these differ so much is that the internal surface temperature, once that is much lower than the ambient internal air temperature, it creates a great disparity. And so because the ICF maintains its internal surface temperature so close to the internal ambient air temperature, Q is very limited, and because it goes down, even though the H is about the same, the temperature gradient is so much reduced due to the temperature change from the wall to the ambient air. And you can notice on the bottom chart that the temperature of the midplane was changed. This is through analysis, the numbers alone. This isn't through the data we performed, but this is taken as an average of the average temperature change of the midplane over time with respect to the actual temperatures measured to the theoretical rho volume and specific heats. So you'll notice that on the left with ICF, it is only losing about 0.13 degrees Kelvin per hour of change, but the R value for that wall system is only 26, whereas the SIP system is losing about 18.55 degrees per hour, and it is rated an R30, which goes to show that the thermal mass is preventing the wall plane from reaching steady state, and so the steady state doesn't apply. Showing our graphs over time, you can notice that in the internal surface temperatures, the blue line is the conventional, and as you can see on bottom, and then the yellow is SIP, and then the gray line basically is right near the surface temperature. And because of that variance in temperature gradient, that's why you see the greatest difference in the Q double prime leaving the walls. And the midplane temperatures are very telling as well, whereas in the second picture down, that's the ICF portion, you'll notice it stays relatively constant because it has so much thermal inertia it doesn't want to change temperature, whereas the bottom ones, the mid-plane of the temperature of the wall stays right around the mid between outside ambient air and the inside ambient air. So it is apparent from this that the R value alone does not dictate the quality of building envelope, and that thermal mass needs to be evaluated and taken into consideration, because the cyclic time of day plays a great role on whether the amount of heat transfer leaving the house is constant, and if it is constant, what can be done to reduce it. So in conclusion, it kind of shows that if steady state was reached, you want the highest R value possible, but the R value doesn't really play an adequate effect until after you've reached steady state. While it's still in transient state, thermal mass is playing a great portion, so it needs to be taken into account.